All right, howdy folks, happy Friday. Welcome back to Pre-Calc. Today we are going to be starting on a new-ish topic. It's going to be similar because we're still solving trig equations, but this time we are adding in the layer of factoring. All right, so you've got a warm-up here. Determine the greatest solution of this trig equation over the interval 0 to 2 pi. I will tell you that this is going to synthesize some of the concepts that we've been using over the past week, so you're going to have to put some pieces together. But I do believe in your ability to do it. So go ahead and pause this video and then come back when you are ready to see the solution. All right, let's see how you did. So we've got a multiple angles problem here. So we're going to sub out 2 theta in for alpha. And then we can see that alpha can be found by doing the inverse cosine of -0.314. And that's going to give us these 2 angle measures on our axes or on the unit circle. And so then I am writing down those 2 solutions, and because we have in the original problem a 2 theta, that means that we need 2 rotations around the unit circle. So I'm going to add on 2 pi onto both 1.89 and 4.393, right? Adding 2 pi onto both of those gives us 8.1 or 8.173 and 10.676. But remember that the question was only asking for the greatest solution. So we really don't need to solve for all 4 of these solutions. We just need to look at the largest number, right? In that case, that would be 10.676. We know that that's equal to 2 theta. And so dividing by 2, we get our final answer here of 5.338. All right, so a little multiple angles here and a little bit of calculator business, but hopefully that went well for you. All right, let's jump into what we are doing today. So here we are kicking off our factoring, right? And that's sort of going to give you a hint. So this prompt is kind of the same for these problems. Solve the equation over 0 to 2 pi. The equation just looks a little bit different because now we've got a whole bunch of trig functions layered up in the same equation, right? But just take a hint from the title. We are going to factor some things. So looking at this equation, 2 cosine theta times sine theta minus sine theta equals 0. You might maybe have the intuition that we should be factoring out the thing that is in common in all of these terms. In this case, that would be sine theta. Right, so we're going to factor out that sine theta. And then in the first term, right, this first term here, that's going to leave behind a 2 cosine theta. If we factor a sine theta out of this term, that's going to leave a -1, and that is still equal to 0. Right, and the big thing here of what we're doing is setting up these factors so that we can use our zero product property. Now that we have this equation in factored form, each of our factors individually is equal to 0. So that means that sine of theta is equal to 0, and 2 cosine theta minus 1 is equal to 0. Right, and then we'll solve each of these equations individually and put together our solutions into one solution set at the end. So for sine of theta equal to 0 over the interval 0 to 2 pi, we're going to be using theta equal to 0 and pi. Right, for 2 cosine theta minus 1 equals 0, you could add 1 and then divide by 2 and get 1/2. Quick maths. So cosine of theta is equal to 1/2, and that's going to occur when theta is equal to pi over 3 and 5 pi over 3. Right, and these are just nice unit circle values. There's really no need for us to be doing things with inverse cosine in the calculator and all that. You should be able to do this with our knowledge of the unit circle. All right, so altogether, that means that, oh, my screen's jumping around on me. Altogether, that means that our solution set is going to be 0, pi over 3, and 5 pi over 3. Right, the only reason I'm using fancy brackets, I don't know if they're entirely necessary, but they're just signaling this is a set, this is a list, and we can mix around the order of those elements however we like. Right, so there is our final answer. All right, let's go ahead and push forward to our next problem here. So I'll scroll on down. Right, I'll also say, for any of these problems, if you just want to pause the video and try them on your own and come back for a solution later, totally fine. you know, you can rock out with that. All right. So if you want to, I guess now's the time to pause, but otherwise we will push forward on example 2. Right, solve the equation tangent squared of theta, right? Remember that this notation right here is telling us the same thing as tangent of theta quantity squared, right? You're squaring the entire tangent function, not just theta. Tangent squared theta. All right, so we're going to be solving this equation of tangent squared theta cosine theta is equal to 3 cosine theta. All right, now here's the thing, and I'm going to change colors here. I'm going to make it in, let's make it an angry red, because this is the thing that you do not do. Capital D, capital UNA, do not say, oh, look, I've got a cosine here, I've got a cosine there, and why don't I just divide out my cosines and cancel, right? Do not do that. You are losing solutions of theta when you divide out entire functions, all right? So do not do this. Then that begs the question, what is it that we are supposed to be doing? What should we be doing instead? What's the proper way to approach this problem, right? Let's first subtract this 3 cosine theta over to the left-hand side, and then we can factor it like we did on the previous problem. So tangent squared theta cosine theta, and we'll subtract our 3 cosine theta to be on the same side. That's going to leave 0 on the right. And now you can see, oh, right, we're going to factor this and we're going to use our zero product property. So looking at this, our greatest common factor would be cosine of theta, so I'll factor that out. And now from here, we've got 2 factors that we can set each equal to 0. So cosine theta is equal to 0, and tangent squared theta minus 3 is equal to 0. And then we solve each of these individually. So cosine of theta is equal to 0. That is true when theta is equal to pi over 2 and 3 pi over 2. And then tangent squared theta minus 3 is equal to 0. All right, we're going to do this first by adding 3 to both sides. So we get a positive 3 on the right. And then we can square root each of these, right, so that we're getting to just tangent of theta. Right, now the key thing here that you definitely need to remember is that when we are square rooting things, especially in an equation, we have to account for signage, right? It's not just going to be root 3. We actually need to account for plus or minus root 3, all right? Do not forget the plus or minus. And so now we need to figure out what thetas have a tangent value of plus or minus root 3. All right, now you might be very, very fluent in your tangent values. Terrific if you are. I know that's the harder one of the 3 between sine, cosine, and tangent. So I'll just give you maybe a few tips here as to how to approach something like this. The way that I sort of think about it is I know that if it's not a root 2 value, then the ordered pairs use a half or a root 3 over 2. And really the only way to get to just root 3 is to have a root 3 over 2, but then divide out the over 2, so to speak. Right, so I'm just sort of rewriting the root 3 in a way that makes sense for what I know of my coordinates around the unit circle. Right, the reason I like writing it this way is because you might remember that tangent of theta is equal to sine theta over cosine theta. Right, so if I'm writing it like this, then I know that I need coordinates or angles on the unit circle where the sine value is root 3 over 2, or rather plus or minus, but the cosine value is some version of 1/2. Right? So let's sort of just zoom in on that. If I make a unit circle, right, where again we said we want the sine values to be root 3 over 2, but the cosines to be 1/2. There's really 4 places where that can happen, and we're going to get a plus or minus sort of deal. Right? It's going to be at these angles around the unit circle. Right? And we can take any of those in any of the 4 quadrants because however it works out, we're covered by the plus or minus. We don't need it to be just positive or just negative or whatever. And so this is going to happen at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All right. So if we were to follow what we did before on our last problem, then we could say that our solution set is going to be pi over 2, 3 pi over 2, and then those 4 angles that we just wrote down in our other equation from our tangent equation. All right. But if those are our solutions, then really what that would mean is that we should be able to take these solutions, right? Any of these, we'll just take one like pi over 2, and we should be able to plug it back into one of our original versions of the equation, and we should be able to get 0, right? That should work out if this is really one of our solutions. So just for, I guess, kicks and giggles, let's hop over to the calculator and see if that's true, right? Now look at this. I have the same the same expression as what we had written at the beginning of the problem. And I just plugged in one of our solutions. We said that one of our solutions, was pi over 2. So I just went ahead and use that as an input. And so if I hit enter, then we should get 0, just as our equation said in the beginning. So I'll hit enter. And then look at that, we're getting a domain error, right? Something has gone wrong in the calculator, and we're not able to actually evaluate this expression. Right now, that's not something that's just happening, something fluky in the calculator. There's actually a math reason for that. So let's hop back to our notes and let's talk about why. Because that solution set of 6 elements is not actually our solution set for this problem. Right, so back in the notes. The reason that we're getting that error is because if you remember about our graphing of trig functions, certain trig functions are undefined. Specifically for our equation here, tangent should be jumping out at you as a function that is discontinuous and is undefined at certain spots, right? The same places where we have asymptotes for these trig functions in our graphs, these are the things that we call restrictions when we are solving trig equations, right? So hopefully you remember that when you have tangent of theta, that theta cannot equal pi over 2 or 3 pi over 2, right? Because if you plugged that theta into tangent, the function would be undefined. And if this tangent is undefined, then the entire equation doesn't work, right? So we need to state these restrictions and then adjust our solution set, right? And be advised, when you take an assessment, we actually are going to give you 2 different answer blanks, one for restrictions and then one for the solution set. So you're going to need to be able to state both of those, right? So I will get rid of this, drop this down here, close up our solution set, and I'm actually going to swap the order. All right. So if we were writing up this answer formally, we would say restrictions. Theta cannot equal pi over 2 or 3 pi over 2. But in terms of solutions, theta can be any element of this set. Or rather, all of these are values that work for theta. All right, so 2 big things here, 2 things to remember. Don't divide, right? If you see something with 2 terms across an equal sign, don't divide, make sure you subtract and factor. And then be on the lookout for your restrictions, right? Be adjusting restrictions as appropriate. All right, so let's go ahead and push to another. Let's keep pushing forward. So solve this equation. 2 minus 2 secant theta minus cosecant theta plus cosecant theta secant theta equals 0. Whew! Yeah, that's a lot. All right, let's sort of break it down into steps though. All right, the first thing that I want you to do, now that we've talked about it, the first thing I want you to do is check restrictions, right? Remember that you're going to be asked for them, so you need to be checking them. if you recognize a trig function that had an asymptote when we were graphing those trig functions, that is a function that you're going to have a restriction on when you go to solve. So you might as well get that out of the way now, right? So let's sort of get in here. You can think about it in terms of the trig graphs. You can also think about it in terms of the unit circle and the reciprocal functions. So secant of theta is equal to 1 over cosine theta. That would mean that cosine theta can't equal 0, right? Otherwise, secant theta is undefined. And the values where that would occur would be at pi over 2 and 3 pi over 2. So theta can't be either of those values. Right? If we're talking about cosecant theta, that would be 1 over sine theta. And so likewise, sine theta cannot equal 0. And that occurs at 0 and pi. So theta cannot be equal to 0 or pi. All right. So I'll just pop these over here, and then we'll clear the deck, and we can get solving on our equation here. Let's write this up real quick. I guess maybe deleting this and shifting this over would be easier. Work smarter, not harder, right? Those are our restrictions. All right, so 4 values that theta cannot equal. All right, now we can go about solving. So we've actually got 4 terms here, and it's not going to be like the previous problems where it was just factoring out a greatest common factor. It's a little bit tougher than that. But think back to things that we've done in the past. What is a factoring technique that we could use if we have 4 terms in an expression? Think about it for a moment. Hopefully some of you have it. This one is actually factor by grouping. I mean, what a throwback, right? Factor by grouping, what a concept. And remember the way that we approached that was we sort of broke it off into groups. So we got a pair up front and a pair out back. And we're going to take the greatest common factor out of each of those pairs. So factoring the 2 and the 2 secant theta, we can see that the greatest common factor there is 2. So I'll factor out a 2, and that'll leave behind a 1 and a negative secant theta. All right. And you know, let's change color here. So let's go purple. And then we need to factor in the back as well, right? It's cosecant theta plus cosecant theta secant theta. And we can see that the greatest common factor is cosecant theta. But make sure that you're keeping track of your signs. So if we were to factor out a cosecant theta from this expression, right, we'd be left with a positive secant theta when we needed a negative secant theta to match up for our factor by grouping to work, right? What this means is that we need to be factoring out a negative cosecant theta to account for signs, right? And factoring a negative cosecant theta out of negative cosecant theta, right, is going to leave behind a positive 1. And that's exactly what we want, because we want this term and that term, right, the entire thing to be matching up. That's how our factor by grouping works. We'll factor out a negative cosecant theta, and that will leave behind a negative secant theta. Right, remember that this is exactly what we're looking for. We are looking for these quantities in parentheses to be identical, and that way we can factor whatever's in the parentheses out as an entire quantity, right? We are factoring out now this quantity inside the parentheses from our 2 terms here and here, right? That becomes our new greatest common factor. Let's go ahead and do that. Let's factor out the 1 minus secant theta. And then it's going to leave behind, from our first term, just a 2. And then from our second term, cosecant theta. Right, and that's going to be equal to 0. And now we've gotten to the point where it's sort of just how it was before. We've got a factored form equation. It's equal to 0, and we can use our 0 product property and solve each of these equations individually. Right? Our first equation being our first factor is equal to 0, and our second equation being our second factor equal to 0. Right, so you can see here that secant of theta is equal to 1. And you could rewrite this if you want to. That would be 1 over cosine theta is equal to 1, which would tell us that cosine of theta should be equal to 1. Right, this is occurring when theta is equal to 0. We are not including 2 pi here because remember in our original interval at the start of the problem, 2 pi was not included. So we're not going to use 2 pi as a solution here. Right? Then we'll solve on this other equation. So cosecant theta is equal to 2. And we can go ahead and rewrite that as 1 over sine theta is equal to 2. I'm just rewriting cosecant theta as a reciprocal. And then take the reciprocal on both sides. So sine theta is equal to 1/2. Right, and again, with our knowledge of the unit circle, that is occurring when theta is equal to pi over 6 and 5 pi over 6. Right, and so now it's time to write up our solution set. But before we throw all 3 of these into those fancy brackets, let's make sure that we are checking our restrictions, because look at that, 0 is one of the values that we cannot have theta be. So this theta equals 0 isn't going to be part of our solution set. We are only looking at these 2 values, right? Pi over 6 and 5 pi over 6, that is our entire solution set. All right. So 3 examples. Hopefully you're getting a sense of how to approach these problems with factoring. I will tell you really, if you got through those 3 examples, you're kind of golden for today. I've got 2 more in the tank here, and I'm just going to add these on at the end of the video. So if you really want to see if you have mastery of this concept, stick around. Or if you want to revisit it later, you're welcome to do that as well. But otherwise, you're totally fine to submit your notes at this point without examples 4 and 5, and you'll be good to go. If you want to see examples 4 and 5, stick around. All right. So otherwise, if this is where some of you head out, then sayonara. If you are here to see 4 and 5, stick around for a bit, and then I'll get started in a hot second. All right, so let's get started on example 4. Right, you can see the equation here, and one thing that's a little bit different from the previous examples is that we only have one trig function. Right, the previous examples had sine and cosine, or tangent and in cosine, or they were secant and cosecant. Right, this one just has sine. And so that actually allows us to break out another old tool from our toolbox. You don't have to use it if you don't want to, but certainly it's available to you. Let's remember u sub, right? U substitution. Because what that did was pick a quantity and just swap it out for a simpler variable, right? U substitution, u sub. Also, did y'all know that in Pennsylvania, they call them u hoagie? That is such a narrow and specific joke that no one's going to understand. Just terrific, just the best. Anyway, you can sub out sine of theta if you don't want to look at it, if you're tired of looking at trig. And we'll bring it back at the end a little bit later, right? But then we just get to rewrite the equation as that, and maybe you find that a little nicer. Maybe that's how you want to roll. Totally fine. U sub. You know, you can rock with it. All right. So if we're going to go about this, we could distribute our 2 into the parentheses. And then I can see a square, I can see a linear u. Let's just get everything on the same side here, right? I'm gonna add that 2u squared over here. We've got a plus u, and then subtract the 2 and we've got -1, and that'll be equal to 0, right? And now it's up to us to factor this equation, or rather factor the expression. Tomato, tomato. So I'll get a box set up. Again, you don't really need a box if you don't need it, but you are certainly welcome to draw it if you would like. Right, we know that we have a 2u squared and a -1, right? And then remember that whatever goes in these 2 boxes, we need them to add to +1 from our middle term, and need them to multiply to -2 from the opposite diagonal. Right, so what are the numbers that add to -1 and multiply to -2? Looks like that would be a +2 and a -1. And those are going to be our u terms. And then going this way, my greatest common factor would be 2. Oh, 2u, mea culpa. And then going this way, my greatest common factor would be +1. And then I can see that if I have a 2u squared and a 2u, I'm going to need a u here. And if I have a u here and a bunch of -1s, this should be -1. All right, so our factored equation is 2u minus 1 times u plus 1 is equal to 0. And then, just like we did before, we're going to solve each of these equations individually. First equation being 2u minus 1 is equal to 0, and then we'll add the 1 and divide by 2, quick maths. U is equal to 1/2. And then u plus 1 is equal to 0, subtract the 1, and u is equal to -1. And now we can just sub back in. Remember that we had u is equal to sine theta. So I'll just sub that back. So sine theta is equal to 1/2. And sine theta is equal to -1. Those values occurring when theta is equal to pi over 6 and 5 pi over 6. And then -1 for 3 pi over 2. All right, so final solution set here, we've got pi over 6, 5 pi over 6, and 3 pi over 2. All right, there we go, example 4. Let's take a look at example 5. One thing you might notice about example 5 is that it has literally the exact same equation as example 4, right? Same equation, but we're going to use just a different technique. I'm trying to pull back some factoring stuff for you just to keep you fresh for now and for next year. It's going to start with much the similar way. Again, you don't need to do this if you don't want to, but you're certainly welcome to. So I'll make a u sub out for sine theta. Right, and then one thing that I'm hoping that you're going to see here is that we've got a 1 minus u squared, right? 1 being a perfect square, u squared being a perfect square, subtraction in the middle. Looks an awful lot like dots, right? Square minus a square. And if you remember your dots factoring, you're going to know that 1 plus u is a factor of that dots, right? That difference of two squares. So we can actually approach this by using difference of two squares, right? And I'm just going to use a different color here just for emphasis. We still have our 1 plus u, and that's on the left, right? Nothing's changed there. I'm just throwing parentheses on it. And then we'll have our 2. And then we can factor our 1 minus u squared using the dots formula. So that's 1 minus u, 1 plus u. Right? And then I'm just going to change the color of the 1 plus u to match what we did on the left, just for, consistency. And so we're noticing we want to get those 1 plus u's somewhere where we can just factor them out. Right? But our factoring is really only good if we have something equal to 0. So I'm going to take that 1 plus u on the left and subtract it over to the right. So let's get all this lined up here. And then we'll subtract the 1 plus u from the left. Right? And now this is super duper, uber similar to what we did with factor by grouping, where we have a term here and a term there. Two distinct terms are separated by subtraction, but they have a greatest common factor of 1 plus u. So we're going to factor out that 1 plus u. Right, 0 is equal to, and we'll make it purple here, that 1 plus u. And then that leaves behind in the first term our 2 times 1 minus u. And then factoring out our 1 plus u from this negative 1 plus u is going to leave behind a -1. All right, now it's just sort of a matter of using our zero product property and then simplifying it, right? So I can say that 0 is equal to 1 plus u, and that would mean that -1 is equal to u, right? I can say that 0 is equal to 2 times 1 minus u minus 1. And then, let's see, I can add the 1 and then divide by 2. And that'll give me the 1 minus u from the parentheses. And then I can subtract the 1/2 and add u. Subtract the 1/2, add u. And then u is equal to 1/2. Right, and then we'll sub back in for our sine theta. So -1 is equal to sine theta. And sine theta is equal to 1/2. If you're recalling what happened just a few minutes ago, those were the same endpoints that we got to in the previous process, and we're going to get the same answers here. So I'm just going to copy my solution set and plop it down here. Right, these are the values where we're going to get sine of theta equal to -1 or 1/2. So there's our solution set. All right, so this really wraps up our video for today. So thank you for hanging out and doing some factoring, some math with me. You're going to just have to submit your notes, but otherwise, have a good weekend, and I will see you next week.